Today we are discussing a very interesting problem in vibration. Actually, this method is called constraint removal method. What is mean by constraint removal method? We are setting some constraint, and for solving the problem we assume that there is no constraint to the system, and we will calculate or we will assess the actual deflection in the absence of the constraint. Now just see a slab that is resting on two springs K1 and K2. Now a force F is applied not exactly in the center, so that naturally there will be deflection at one end will be more and deflection at other end will be less. But this particular problem is solved in such a way that the bar remains horizontal or parallel after the application of the force. That means instead of x1 and x2, the deflection of the bar is x. We know that normally there will be deflection x1 in the left and x2 will be in the right. But because of the unique nature of the stiffness of the springs, the entire bar remains horizontal and that deflection is x unit. We have to find out the equivalent stiffness of the springs and also the deflection of the bar from the initial position. Now simply see the deflection x is equal to x1, that is the minimum value, plus a divided by a plus b into x2 minus x1. That means the length ratio is multiplied by the difference in the deflection. Now rearranging the deflection, we get ax2 divided by a plus b plus bx1 divided by a plus b, because ax1 minus ax1 terms will cancel out. Now it is very interesting that the total downward force is F and the total upward force is F1 and F2. That is, F is equal to F1 plus F2. Similarly, taking the moment at the point F, F1A equal to F2B. Now we are going to the next level. That means we are taking moment at the extreme left point and also moment about the right point. What will be the left point if you take the moment F2 into A plus B, that is equal to F into A. That means F2 equal to FA divided by A plus B. Now what will be the moment if you take about the point F2? It will be F1 into A plus B, that is equal to F into B. You will get expression for F1 and F2. Now we know that stiffness is equal to force divided by deflection, or deflection equal to force by stiffness. We will get expression for x1 and x2, that is the deflection in the left and right point. Substituting x1, x2 in the standard equation derived in the previous slide, we get expression for x. That means the actual deflection of the bar from the initial condition, that will be F divided by A plus B whole square into K1 K2 into K1 A square plus K2 B square. Suppose you want the equivalent stiffness, then that expression is F divided by X, that is equal to F divided by X equal to A plus B whole square into K1 K2 divided by K1 A square plus K2 B square. So it's a very unique problem. Even though the load is not applied exactly in the middle, the bar remains constant, and throughout the bar the deflection remains the same. And the strategy adopted in this particular solution is sufficient to find deflection and also the equivalent stiffness of the system.